let's get started. Okay, I'm just going to mute everybody. All right. So welcome to week 12 of AI612, Machine Learning for Healthcare. So today this week we're going to talk about multimodal learning. So last week we talked about medical images. So we started with the different types of medical images, such as X-rays, MRIs, CT scans, fundus photos, skin photos, all kinds of different photos, like 3D, 2D videos, whatever. And then we briefly talked about image classifications using Inception version 3, actually. So those were mainly the work done by Stanford and Google around the same time as 2016 for skin cancer detection and retinopathy detection. So those were that was pretty simple. And then last Thursday we talked about image segmentation. So we talked about like what's the difference between like object detection, localization, image segmentation, instance segmentation, semantic segmentation, all that. And then we talked about UNet, which is probably the most popular model or tool for doing semantic segmentation, which was developed for biomedical image segmentation first, but now it is being used like all around. So the architecture was just a simple encoder decoder base. So that's why it's called UNet. So you first compress the image into latent, you compress the image into smaller, spatially smaller, but depth-wise larger. And then you decompress it, or you expand the compressed features into the original feature. And at the last layer, you use one-by-one convolution to do a classification basically per pixel. So you try to classify each pixel into different classes, such as different objects. So like background and liver or heart or lung or different kinds of stuff. So that was that. And this week we're going to talk about multimodal learning. So the first is we're going to talk about vision and text. So today we're going to talk about vision and text. So multimodal learning typically started with vision text multimodal learning since 2019 and 2020. So a lot of people, but even before that, there was a lot of works that can be thought of as multimodal learning. But these days, when people say multimodal learning, they mean usually just using a pre-trained model. So we're going to talk about that first, and then dive into chest X-ray and radiology report multimodal learning. So we already covered a data set called Mimic CXR. So Mimic -CXR, which consists of about 30,000 chest X-ray images with a paired radiology report. So it's a lot of vision text samples. So we're going to first take a look at what would happen if we do multimodal learning using the two, and then hopefully we can finish that today. And then this coming Thursday, we're going to talk about graph and text. So we've already covered how electronic health records can be seen as graphs because electronic health records are typically stored in relational databases in the hospital, and then you can actually rearrange or restructure the relational database tables into a single gigantic graph. So we're going to look at how we can train graphs and text at the same time using EHR and its discharge summary. So the discharge summary is what you guys are using right now for project number 2. All right. So multimodal learning first. So when we say multimodal, we mean multimodal. So what we mean is that there are at least a lot of different modalities, and modalities usually, to my understanding, modality means different data types. So for example, like people usually say images and text are of different modalities. So they are two different modalities, image and text. And obviously, graphs can be seen as another modality. So because it is structured, so unlike a sequence of pixels or a sequence of tokens or a sequence of words, graph has a specific structure. So these are usually called unstructured data, image and text. Graphs are usually called structured data. And in the same manner, database or tables are structured data. So some people might say that tables are also another type of modality. But then, as I said, tables and graphs can be seen as, can be interchanged, are or can be used interchangeably. And time series data or multivariate time series data can be seen as another type of modality. So none of these, like what this are, they're all different from multi. Sorry, I think my Wi-Fi just got disconnected for like one or 2 seconds. Give me just maybe 5 more seconds, please. Sorry. All right. Everybody can hear me? All right, cool. Yeah. My Zoom says that my internet connection is unstable. This is really annoying, actually. All right, yeah. So back to the slides. I am sharing the slides, right? All right. Okay, so slides are okay, right? Let's continue. So as I said, the multivariate, so all these images, text, graphs, and multivariate time series they're all of different modality. And some people might say that videos, such as YouTube videos, are of different modality than images, because images are just, they are static and videos are dynamic. So videos can be seen as a sequence of images. So people might say that videos and images are also different modality. So modality is basically, and some people even might say that actually, let's talk about health records first. So in healthcare, there are also a lot of different modalities, such as a sequence of structured codes. So this is what we actually used for project number 1. So we kind of actually not exactly project number 1, because this is more like outpatient focused diagram. So for example, like a patient comes to the hospital and then receives a bunch of medical events, such as diagnosis codes, medication codes. So these are, and there is a sequence of visits. So these are based on codes, which are typically structured. So you can actually build this kind of diagram from the relational database, so the table. So this is you can think of this as a structured information about the patient, but it has temporal information incorporated. And compared to that, continuous values such as blood pressures or vital signs like respiratory rates or heart rates or SpO2, which is a saturation level of the oxygen, such things like that. Those are a bit different from the structured codes. Those are kind of like multivariate time series data. So that is another modality. And then EKGs, or actually EKGs are also time series data, but you can convert them using Fourier transform to obtain the spectrogram that looks like this. So this can be seen as another modality. Obviously, the text that you guys are using right now for project number 2, text is another modality. So discharge summary or nursing notes, physician's notes, radiology reports, consultation notes, all kinds of things. They are different modality. I mean, they are just free text notes, so they are of different modality than all these different, structured codes or time series data. Images are obviously another modality. So X-ray images, CT scans, they are just, they're based on pixels. So as none of these are based on pixels, so that images are of different modality. So what I was trying to say in the previous slide is that some people would consider, for example, diagnosis codes and medication codes as different modality, because they actually mean different things. Diagnosis is about disease, it's about symptom. 이제 진단이랑 약은 다른 정보다, 다른 모달리티다라고 생각하시는 분들도 있을 수 있다는 거죠. 네. So even though they're of the same structure, they are still both structured codes, because diagnosis codes are codes and drugs are usually represented as codes. But some people might say that semantically they're different. So some people might say they're different modalities. So I guess the definition of data modality is a bit subjective. It could be based on purely the surface form, whether it's pixel based or whether it's pixel based or code based or word based, but to some people it might be a bit more semantic. So like disease and diagnosis and medication could mean different things, or maybe X-ray and skin photos can be different modality, even though they're still 2D images. Some people might consider them different modalities. So I guess it depends on what you consider as data modality. Okay, so so given this context, given this a bit vague definition of modality, we'll continue. So even before like 2019, the explosion of vision text multimodal pre-training models, all BERT-based, even before that, way back in like 2015, 2014, 2016, people were already doing multimodal learning or different form of multimodal learning, such as image captioning shown here. So these are examples from show and attend tell. So obviously show and attend tell was even before this, there was show and tell, obviously, because show attend tell is just it is adding the attention mechanism on top of show and tell. So before that, so probably like in the early 2015 or maybe late 2014, people are already trying to do multimodal learning, which or image captioning. So it is I'm not sure if, I guess it depends on what you consider a multimodal learning, but obviously the model is using two different modalities, image and text. So given an image, the model is receiving the image and outputting or generating a caption, generating a text that describes the image. So these two, the pixel and text or words, are expressing the same semantic information, same information basically. The contents are the same. It's just that one uses pixels to represent the information, and another uses words to express the information. And so you can think of this as like encoder decoder. So encoder decoder operation. The encoder is to encode the images or pixels, and decoder usually decodes into a sequence of text. And this part, the black and white part, is just example of just attention behavior analysis. So here, a little girl is sitting on a bed with a teddy bear. So the girl, the word girl, is attending to this region, and a group of people sitting on a boat in the water. So the word people is also attending to this region, and trees, the word trees is attending to all other, all the regions except for the giraffe. So the model is doing a pretty good job. So if image captioning can be seen as multimodal learning, then obviously image generation based on text. So it's a text to image. So conditional image generation also can be seen as multimodal learning. So back in 2016, there's a work called text to image GAN. So you are basically conditioning the GAN to generate images based on a given text. So it is using LSTM to encode the text and then push that into the generator, and also use the same text to as part of the discriminator, because you want the discriminator to both to consider both the textual information and the image information to to discriminate from the real image from the fake images. So so the left column here is the ground truth, and the text here is the given text for the ground truth image, and you can see that the generated images are, it's not that much of high quality, but you can kind of see what the model is trying to express. For example, here a pitcher is about to throw the ball to the batter. So obviously this is ground truth image, and you can see these 6 small generated images or synthetic images, and the shapes are not exactly people. It's not exactly the baseball players, but the field, the baseball field, like here, there's like grass, and then there's pitcher mound and some. I'm not sure what this is. I don't know. Like maybe trying to express like second mound or something. I mean, you can kind of feel like you can kind of understand what it's trying to express. So you obviously you cannot understand that the pitcher is about to throw the ball to the batter based on this image, but you can at least understand that it is trying to draw a picture or generate a picture of players playing the baseball. Same here, like a man in a wetsuit riding a surfboard on a wave. So this is obviously the ground truth image, and if you try to read these generated images, you can kind of see that it is the sea, it's the ocean, and there's a wave, and then there's a person trying to do something. I mean, based on like this or this or this, I guess it is a bit hard to understand, hard to capture that there's a surfer, but at least you can see that the model is trying to draw a picture where a person is playing in the ocean. So yeah, so that was back in 2016, and this was already kind of already impressive enough back in the 2016 standard. So there has been a lot of work after, so work that follows this work, text to the image scan, and the most recent effort is obviously from OpenAI. So in 2021, so I think this year, so about a couple months ago, I think it was February or March or something. So late February or early March in 2021, OpenAI announced a work called DALL-E. So it's kind of like WALL-E from the Disney animation. I'm not sure why they call it DALL-E. Anyway, so again, a mind-blowing work from OpenAI after GPT-3. So if you read, so these are all generated images. First of all, none of these are ground truth images. So the model has never seen this kind of image before. So given this, for example, let's look at this image. So given this, an illustration of a baby hedgehog in a Christmas sweater walking a dog. So the model, after being trained on like millions or trillions of images collected from the internet, the model is trying to generate an image that corresponds to this description. So the model receives this text and then tries to generate images. And obviously the model has never ever seen a textual description like this before. So this is a zero-shot image generation. And the quality of the image is just, it's just mind-blowing. It's phenomenal, impressive. So this is obviously not a photographic image, but it's an illustration, but the given text was what it commanded. It requested an illustration, not a photographic image. So it is doing exactly what is being asked for. So there's a hedgehog, and then it is walking a hedgehog. So I guess this is an incorrect image, but this one is like very, very accurate. So there's a hedgehog in a Christmas sweater. So it looks like a Christmas sweater. The color says, green and red. So Christmas sweater is walking a dog and dog. This is also, obviously the model is being asked to generate images that describes an object that doesn't exist in the real world. What is this? This is an animal called tapir. Not sure what tapir is. It looks like a 개미핥기 같이 생겼죠, 아마. Let me see. A tapir is a tapir. It's called tapir. Tapir. It's 한글로 맥이네요, 맥. 맥이 뭔지 모르겠는데. It's a hoofed mammal. Hoofed mammal. 그러니까 그 발굽이 있는 포유류라고 합니다. Lives in the forest of tropical America in Malaysia. 글쎄 뭐 맥이 뭔지 잘 모르겠는데. 네. Anyway, so it is a tapir made of accordion, which obviously doesn't exist in the real world, but the model is doing a phenomenal job. It actually is able to draw a tapir that has a body of an accordion. So obviously doing a phenomenal job. This here as well, like a backprop, a neon sign that reads backprop. So nowhere in the world is there a neon sign that reads backprop, or I guess that's a strong point, but you can I'm pretty sure there is no such thing as a backprop neon sign, but the model is doing a pretty good job doing drawing a backprop neon sign. So you can see how expressive, or how the like virtually infinite capacity of this model, DALL-E. So this can be, I guess, this can also be seen as a form of multimodal learning. And lastly, another type of multimodal learning, or early multimodal learning, is visual question answering. So I guess this is a bit more, even more multimodal than previous examples. Previous examples being like encoder decoder approach. So either you encode the image and decode into text, or you encode the text and decode into image. So those were the two previous examples. VQA actually needs to understand both text and image at the same time. So you need a model that encodes both image and text at the same time, and then mix the information, mix the encoded representation somehow, doing either co-attention or like bidirectional attention or whatever, and then the model needs to answer or generate the answer to the question. So here, what color are her eyes? And the answer is black. And what is the mustache made of? And the answer should be banana. So it could be a multi-choice question, or it could be a purely generative question. But this is another early form of multimodal learning. And these days, actually, when people propose a new pre-trained model for multimodal learning, they usually use VQA as a downstream task. And obviously, they can use other conditional image generation or image captioning as another form of downstream task. But usually, VQA is like the go-to task for a downstream application. All right, so after several years of this type of multimodal learning, like image captioning, image generation, VQA. So which were all born in 2015. So after several years, but that has been going on. Those kind of effort has been going on for quite a while. And then after the birth of BERT, which was proposed in 2018. So people are more interested in now to come up with a model, a pre-trained model that was pre-trained both on on multiple modalities, typically vision and text, that can do a lot of downstream tasks well at the same time. So just like BERT has, once you have the BERT like off the shelf BERT model, you can fine tune it on any downstream test NLP test you want. So that's what BERT was known for. So in the same spirit, you want to have a multimodal vision text pre-trained model which you can use like an off-the-shelf product, and then you fine-tune that pre-trained model for any multimodal downstream task you want, which can be, as I said, image captioning or image generation or VQA. And obviously, you want the performance to be, you want the fine-tuned pre-trained model to outperform all the other models, such as previous encoder decoder approaches, or VQA approaches, such and such. All right, so let's take a look at the. I'm sorry. Yeah, let's take a look at the BERT-based pre-trained multimodal learning. So just to recap, so what BERT is. So BERT is just a gigantic stacks, gigantic layers of transformer blocks, transformer encoder blocks, actually, because the original transformer consists of encoder and decoder. So BERT only uses the encoder part of transformer. So you stack multiple transformer encoders, originally 12 layers of transformer encoder, and simply you just mask the input token and then try to guess what the identity of that mask token is. So here, like, my something is cute and he likes play something. So the original text would be dog and playing. So sharp ing, and this should be dog. And so BERT, I mean, this is the main task, MLM, obviously, as you guys already know. But there is another task called next sentence prediction, which is based on the CLS token here. So originally BERT receives two sentences. So here the sentence number 1 is my dog is cute, and the sentence number 2 is he likes playing. And the next sentence prediction task is trying to use the CLS token, which is the special token, to classify whether these two sentences are consecutive or not. So whether they're like which is to try to classify whether the two sentences are neighboring or not. So here, semantically, my dog is cute and he likes playing is naturally they are, they make a lot of sense when they're put next to next. So I guess, so probably the CLS token, the true label for the CLS token is 1. But if the given sentences were like my dog is cute and for example, like what is, like, people are buying a lot of Tesla cars. Those two sentences are, like, very much independent. So in that case, the CLS token ground truth label should be 0, something like that. So it's trying to capture a bit more high level semantic compared to just trying to capture token level semantic. So there are 2 tasks. So, and a lot of vision text multimodal learning exploits or utilizes these 2 tasks. Although in BERT, people don't usually care a lot for the NSP task, especially for, like, if you think about Roberta doesn't use NSP. It only uses MLM to pre-train a gigantic BERT model. So people usually don't put a lot of weight on the next sentence prediction task. But in multimodal learning, people do put some, like, not a lot, but more weight on the NSP task, or should I say, like, image text alignment task. All right, so given these 2 tasks, we're going to use it for pre-training a vision text multimodal model. So there are a lot of BERT-based vision text models since mid 2019 all the way to, like, late 2020. So there's like Video BERT, VI LBERT or VilBERT, InterBERT, Uniter, Pixel BERT, and I forgot to mention here, but there's also a unified VLP. So I'm not sure what that's short for. Unified VLP is like Unified Vision Language Pre-trained Model or something. So, like, there's a lot of different variants, but they are all based on these 2 tasks. So obviously they're based on repeated layers of transformer encoder, and then they somehow use these 2 tasks to pre-train the said model for vision text multimodality. So let's just look at them one by one first. Briefly, I can't go into detail for all 5 models. So we're just going to take a look at the high level ideas and then try to see how you can use it for chest X-ray and radiology report as well. So in Video BERT was presented in ICCD 2019. So but I think it was first uploaded on arXiv around like April or May 2019. So that's already like 2 years ago. So, and interestingly, this wasn't based on image. I mean, this is image text, but it wasn't based on 2D images. It was based on actually a video. So this was so VideoBERT was proposed by people from Google. So they took the YouTube images, especially the cooking videos or like recipe videos. So they just after collecting a lot of cooking videos along with its captions, they try to do a multimodal pre-trained learning using BERT architecture. So you can, in these days, a lot of videos come with captions. So, and captions usually stay for a couple of frames, like if you think about like 30 frame per second video, like 30 FPS video. So a single second consists of 30 frames or 30 2D images or 30 2D images, and the caption usually lasts for a couple of seconds, like 1 or 2 seconds. Like if you think about the cooking video, it's usually like like a main character, a cook or chef, is either like slicing the onions or or grilling the steaks or whatever. And so, and as the chef is doing some kind of action, the caption is usually like, please dice the onion like into small pieces, something like that. And then the chef is, moving the knife around. So that usually takes about a couple seconds. So if you think about 30 FPS video, it means that the caption lasts for about 60 to 90 2D images. So what you can do is you can actually sample out of those 60 or 90 2D images, you can sample a couple of 2D images, and then match that with a given caption. So that's what's happening here. So place the steak in the pan. So obviously the chef is, putting the steak into a frying pan. So it's a steak cooking video, and then you can imagine a movement, like a continuous action where the chef is picking up the meat, the steak, and then moving it into the pan, which would probably last about 1 or 2 seconds. So you can sample a still image out of 60 to 90 frames, 90 2D images. And if for example, if this was a 60 FPS video, then you would have a 120 or 180 sequence 2D images to sample from. So here they sample about I'm not sure exactly how many 2D images they sample from for a single caption. I think they do it about probably less than like 256 or something, because the original BERT had like 512 tokens. So yeah, so they would probably want to match the maximum length for both text and images. And for encoding the images, they discretize the image into some codes. So like each pixel, each image corresponds to some code, like a word. So they don't have note that there is no CNN. So they either use like discretized VAE or that kind of like discretizing or quantification algorithm to quantify or discretize the pixels into a set of codes. So similarly to like lookup embeddings for your words. So your words are transformed into a continuous vector. An image is also transformed into a continuous vector. So both are actually just token embeddings basically. And then basically you do a lot of self-attention, and then you put a mask, and then you just simply do mask language modeling. So here the mask, given like place the steak in the pan, you randomly mask like 15% of the text and 15% of the sampled images, and then you try to guess or reconstruct its identity. So here you want the model to predict the steak, and here you want the model to precisely predict the encoded predict the token embedding of this image, and that's it. So that's basically it. So given that after pre-training this model a lot for using the mask language modeling, what you can do with this video BERT is basically just you can generate captions. So as the video is being streamed into the model can actually create captions, and it is doing a pretty good job actually. So here, given two sequence of images, the model needs to generate the captions, and the ground truth caption is add some chopped basil leaves into it. And what video BERT says is chop the basil and add to the bowl. So there is no bowl here, but contextually, usually basil is put into the bowl, I guess. So that's why the video BERT decoded the bowl after the basil and add to. S3D is the previous state of the art, and obviously it's not doing a pretty good job. Like, cut the tomatoes into thin slices, and nowhere in this picture is there a tomato. Another example. So here, the ground truth is that actually what's happening in the images or in the sequence of images is that the chef is kind of like is peeling the top of a baguette, I think, to maybe so that he or she can later stuff the baguette with some ingredients. So it is not actually slicing or cutting. He or she, the person, is using their fingers to, slice or like peel off the top portion of the baguette. And the video BERT says cut the bread into thin slices, which is not exactly true, but it is doing a better job than S3D, which says place the bread on the pan. So there is no pan here, and obviously the chef is doing something with the bread. So in that context, in that semantic, video BERT is doing a better job than S3D, and so on and so forth. So here, cut yu choi. I'm not sure what yu choi is. I think some kind of like a Southeast Asian plant, I guess. So doing something with the plant, and then it is doing a better job. Video BERT again doing better job than S3D. At least the video BERT says cabbage, which is not exactly yu choi, but cabbage is still plant, and it's better than cut the roll, which roll I guess is like a bread roll, so on and so forth. So this was the early form, one of the very first multimodal model based on, interestingly, video and caption. And around the same time, NeurIPS and Vilbert was presented in NeurIPS, but so NeurIPS is way back. NeurIPS is usually held in like December in each year. So timing-wise, Vilbert was officially proposed or officially presented later than video BERT, but they were both like uploaded on archive around the same time. I think there was a question. Question from 준민님. 이미지 데이터는 기존 버트 단어에 사용되는 세그먼트 임베딩 등을 추가하자 그들 인풋을 들어가네. 좋은 질문입니다. 세그먼트 임베딩 다 추가됩니다. 포지션 임베딩도 추가될 수도 있고요. 아마 제가 비디오 버트의 자세한 그 페이퍼를 읽진 않았는데 아마 그 순서도 추가가 될 수가 있겠죠. 왜냐하면 비디오는 특히나 순서가 존재하니까 이제 우리가 이미지를 캡션 하나당 이제 보통 아까 말씀드렸듯이 60프레임에서 90프레임 정도의 이미지가 주어지고 캡션 하나당 그 안에서 이제 랜덤하게 몇 개를 샘플하거나 다 넣을 수도 있겠죠. 사실 90프레임이면은 90 토큰밖에 안 되니까 버트가 512 토큰을 처리할 수 있다고 치면은 다 넣을 수도 있겠죠. 근데 넣을 때 이 프레임마다 순서가 있잖아요. 이미지 프레임마다 이게 이제 그거를 이용을 안 할 이유가 없죠. 그래서 포지션 임베딩도 넣고 세그멘트 임베딩도 넣어야 됩니다. 그래서 이제 요만큼 세그멘트 임베딩으로 요만큼은 텍스트고 요만큼은 비디오다를 이제 추가를 해줘야겠죠. 네. So that was a very good question from Junmin. So the question was that do you still use the segment embedding just like the ones that you use for BERT for indicating the first sentence and the second sentence? You can use segment embedding for video text multimodal models. So you can use segment embeddings to indicate like certain subsequence is text and certain amount of subsequence is video or images. So all right, moving on to Vilbert. So Vilbert is so previously VideoBert was using YouTube videos and caption. Vilbert just uses images and caption. So still image, just one image and one caption. So given an image and a caption, what Vilbert uses is first pre-process the image using faster RCNN. So it uses a off-the-shelf object detection model to extract relevant objects from the image and then encode that into a fixed size vector. So that was basically using faster RCNN. So using faster RCNN would have like a would extract boundary, like a box for each object in the image, and then that box can be converted to a fixed size vector to represent as like a feature representation of that box, and then that can be seen as another token embedding from the image. And obviously the text part is just token embedding. You can just convert them into token embeddings using a lookup table. So here, this image tokens, like here, these are all from the same image, just extracted by the object detection algorithm. And here, this part is just it's just a caption for the image. And when the object detection algorithm, such as faster RCNN, extracts objects from the image, it usually comes with a object classification label, classification output. So for example, like if it is based on usual, I'm not sure about how many classes the faster RCNN classifies a given patch into, but if it is using ImageNet classes, then there are 1,000 classes that a certain patch or a certain object can be classified into. So instead of doing mask language modeling like here, instead of doing mask language modeling for both text and image, here in Vilbert, mask language modeling is only used for the language parts, only the text part. And for the video part, for the image part, what they do is given an image, you try to classify the image into its original classification output from the object detection, the base, i.e. faster RCNN. So you're just, so as I said, faster RCNN, when extracting objects from the image, it comes with a distribution of class distribution or label distribution, and you're simply reusing it here for pre-training the text part, the image part. So you mask it and then try to reconstruct or classify into the label distribution from the faster RCNN. So that's how you do how you train Vilbert. And as I said, there is another task called image text alignment. So which is the same as next sentence prediction. So here you have the special image token and the CLS token. So the CLS token is used for the text, and image token, ing token, is used to represent the entire images. And using these two, so you concatenate them, or you either do inner product or whatever. But basically, you take these two special tokens and then try to classify whether these images and these text tokens are from the same pair. So whether they're aligned or not aligned. So basically, that's it. So you do two pre-training tasks. One is mask language modeling. And mask image classification, and then image text alignment. That's it. So basically they do visual question answering with this model, and then obviously it performs better than previous state-of-the-art models. So there's something called Interbert again. So Interbert is a bit more complicated than the previous two models, which were Vilbert and VideoBert. So it has modality specific encoder. So there's image embedders, and then there's text embedder, and then there's like a cross model or multimodal embedder in the middle, using basically using self-attention mechanism. So basically, this is just another variant of BERT, or variant of a transformer. And then at the top, interestingly, at the top, there is again image extraction module and text extraction module. So unlike the previous two examples, like here, this is just one model, and then they just have an output, CLS output, and set token. They just have a CLS output, and that's it. And here in Vilbert, there's image token output and CLS token output, and that's it. There is no further processing of the contextualized features. But here in Interbert, there's further processing for extracting image-specific feature vectors and extracting text-specific feature vectors from the contextualized output from this gigantic self-attention model. So they use those modality-specific extraction module to do some, pre-training objectives, mask language modeling and image text classification and mask region modeling. Mask region modeling is the same as doing this here, because Interbert again uses faster RCNN to extract objects from the given image. So the basic approach is more or less the same for all these models. It's just that not all, but Interbert and Vilbert, they're very much similar. Given that they both use faster RCNN to extract object-specific features from the image, and then trying to do mask language modeling, and then trying to do image text alignment alignment loss as well. It's just that Interbert has one more layer, which is modal modality specific extraction module. Another gigantic model is called Uniter. So Uniter, I'm not sure if it was presented in any conference. So Interbert was presented in KD 2020. So I'm not sure if Uniter was presented anywhere. I think it was submitted to iClear and then it got rejected, but it still is in archive. So it's a bit more, it's more or less the same. It's just that it has a different modality specific encoder. So here, it is still using faster RCNN. So it is using object detection, off-the-shelf object detection model to extract objects from the image, and then pushing that into a gigantic layers of transformer. But before pushing the object features and textual features into the transformer, they have a specific image embedder and text embedder. So here in the image embedder, they have a RCNN feature and the location information put through a fully connected layer or feed forward network, and then summed up, and then just doing a linear transform or whatever lookup embedder, and then that's the final image feature. Similarly to here, they have a token embedder and position embedder, and then do text feature embedding, which is semantically more or less the same as before. Like all these, like Interbert, Vilbert, they more or less use segmentation embedding and position embedding. So it's not that much different. And then they do 3 different types of pre-training tasks, which is obviously one is mask language modeling. So here they only do mask language modeling for the text part, and then they do mask region modeling for the image part. So here, I'm not sure what they exactly do. I'm not sure. They probably use some kind of they probably use the object feature extractor from the original image. So the output of the faster RCNN to reconstruct the masked region or masked image token. And thirdly, they do the image text matching. So here they only use one CLS token instead of like in Vilbert, where there was image token and then the CLS token. There's only one CLS token, and then they use this CLS token to classify whether this given image and text is matching or not, or is aligned or not. So again, all these like Uniter, Interbert, and Vilbert, they all use faster RCNN to extract object-specific information from the image, and then they do basically three pre-training tasks. One is masked language modeling, and then another is masked image modeling, and then the third is image text alignment classification. And it's just that they have slightly different objectives, slightly different model architecture, slightly different input encoding. And then this is a bit qualitative example from the Uniter. So what they're doing is image captioning and using the pre-trained uniter. So using the pre-trained uniter, the authors fine-tune the uniter to perform image captioning. And here is given an image, a girl with striped shirt is sitting on a bicycle. So this is what the model has, generated as a caption. And for each caption, right, I mean, each token or each word in the caption, you can see where it is being, where the model is attending, where the token is attending to. And the token is attending to, obviously, object detection, object boundaries, because here, here to the model is given object boundary or object, individual objects extracted from the FASR RCNN. So, and it is being, the self-attention is applied to both the objects and the text at the same time. So when doing image captioning, the text is able to attend to individual objects from which is the output of the FASR RCNN. So here, the girl object, the word girl or the token girl is attending to this box where the girl's head is, and then striped, the word striped is attending to this box, this object box, extracted from the FASR RCNN, which is striped shirt here or striped clothes. Shirt again here, sitting is a bit attending, the attention is a bit more spread out, and then the bicycle is attending to this box here. It is doing a pretty good job. Same goes with a man and child working on a puzzle. So the puzzle is tending here, child is tending to this box, a man is tending to this box. It is doing a pretty good job. And lastly, so this is a bit different from the three previous works, which is three previous works being Wilbert and Interbert and Uniter. So here, no object detection module is used. So previously, FASR RCNN was used all the time, but here in Pixelbert, which was also uploaded in archive in 2020, but I'm not sure if it was presented in any conference or journals or anywhere, but still in archive. And it is not using any object detection algorithm. So it is just purely data driven. So a text is given, obviously. So this part is the same as all the other models, but here this part is different. So they use, so given an image, they use ResNet. I'm not sure if this was ResNet 50 or ResNet 100 or if it was DenseNet or whatever. I'm not sure. I think it was ResNet. So let's call that a ResNet. So the image is pushed through the image ResNet, and then finally there's right before global average pooling, there's like a layer below the global average pooling, where you have a spatial dimension still alive, and then there's like a channel-wise depth as well. So it's a single image is transformed into a 3D tensor, where the first dimension is height, second dimension being width, and the third dimension being depth or kernel or the channel number of channels. So basically, it's a set of fibers. So when you spread out, when you flatten the width and height, basically you have a matrix where each column is a image feature fiber. So you have a set of fibers, and then basically you just put those fibers, image fibers, into a transformer, and that's it. So here the words are transformed into token embeddings using position embedding, semantic embedding, token embedding. You sum them up, and then you basically get the token embeddings, and it's ready to be input into the model. And you have a fiber, and you need to match the dimension of the fiber into the dimension of the token embedding. So basically, I think it was like, I don't know, 768 or maybe 256. I'm not really sure, but they're like, you have a fully connected linear layer to adjust the dimensionality of the fiber. Here, the semantic embedding is also given here as well. So, and what they do is interesting. What they do is they don't put all the fibers into the transformer. They sample the fibers. So, given, for example, like if there are, I don't know, like 7 by 7 by, so like right below the global average pooling, let's say that there's like 7 by 7 height and width, 7 by 7, and then 512 depth, then you have 49 fibers, right? And then out of the 49 fibers, you roughly sample only 40 fibers, and that's it. So it's like doing a dropout or like masking, actually. So you're dropping out certain number of fibers, and you only retain remaining fibers, and then put that into the transformer. So this is it, and there is nothing else. And then the pre-training tasks are mask language modeling. So they only do mask language modeling for the text part, because you can't do anything with the images, because they don't use any object detection. So there is no per object or per fiber class. So you can't do anything with the fibers. You just do mask language modeling for the text part, and then there's image text matching as well. So you just have one CLS token, and then using this CLS token, you can do image text matching, and that's it. So only two pre-training tasks. And interestingly, it does work to some extent. So they do a lot of like image capturing and VQ and that kind of stuff. Well, let's take a look at only the qualitative examples. So here, what they do is given a dog and a caption, they're trying to see if the text and the images are, if the text is grounded on the pixel image, basically. So here, the given text is a dog sits on the grass with his frisbee, and the image is, again, a pixel representation of that. And here, the word dog is actually attending to the dog a lot, compared to all the grass part is all blue with very low attention score or low attention weight, but the dog is getting all the attention, and the word grass is attending to all these parts. So, and the frisbee here, there's a frisbee here. The word frisbee is attending to these pixels. So here, compared to this, where the word is attending to object boxes, here the word is attending to pixel regions, because there is no box here. You're just putting the pixel fibers into the model in that sense. So you can just basically see you're just tracking how the tokens in the word is attending to different fibers, and that's it. So here, the grass is attending to these fiber, and the word frisbee is attending to this fiber specifically. Same with the second example. Here, the given caption is a man cutting up carrots in long strips, and the word man is attending to the hands to the hands of the man, interestingly. And then the word cutting is actually attending to the knife part, and the word carrots is attending to the carrot part. So it's doing a pretty good job, actually. So even without the object detection off-the-shelf object detection module, the model can, just by doing a bird type pre-training process, just by doing a self-attention with mask language modeling, the model is able to connect the words into pixels. So it is the word grounding is occurring no matter what. So I thought this was a pretty impressive output. Not sure why the authors are not submitting this work to any conferences. All right, so far, so this is more like a daily general domain vision text multimodal learning. And we're going to take a look at how this can be translated into chest X-ray and radiology reports. So far, any question before we move on to the next part? Nope. Okay, so let's move on then. So what we're gonna see is what happens if we apply, or if we just simply apply Pixelbird into chest X-ray and radiology report. So we've already covered what Mimic CXR is. It consists of about 377,000 images with a matching report. So it's an image and text pair. So and I briefly described this, but a single note or a single report is paired with multiple images, potentially multiple images. Like like when you go to the hospital, when you take an X-ray, you take the frontal view and the back view, and sometimes you take the lateral view. So here, a single report can come with multiple images. But in this example, we're gonna see just one image and one report pair. So we're just going to take a look at the frontal image with its matching report, and that's it. So no multiple images per report, just one image per report. So for example, we're going to only look at the frontal view, and the text report looks like this. And usually only the findings and the impression part is used, because all the other parts are kind of irrelevant. Those are just meta information, such as the date of the date and time of the image, well, date and time when the image was taken, or the name of the patient, or the name of the doctor. So those are irrelevant. So usually only the findings section, where there's lengthy text here, and the impression section is used as the textual input to the model. So model is basically what we can do is putting the chest X-ray image and the radiology report into a stacks of transformer, so sequence of transformer. And using mask language modeling and image text matching. Given a pre-trained model like this, you can do a lot of a variety of downstream tests, such as diagnostic classification. So given an image and a text, trying to classify what kind of disease the patient has. Image text retrieval, which is given an image, trying to retrieve the most relevant report, or given a report, trying to retrieve most relevant images. So it's kind of like Google image search. And visual question answering, obviously you can do this for medical. So there is a medical visual question answering data set. So you can obviously apply this pre-trained model for this downstream test. And you can also do vision language generation, specifically image captioning. So given a report, you can try to generate, given an image, you can try to generate the report automatically. So a lot of downstream tasks. So the model architecture is pretty much the same. So you have a image put through a ResNet, and then you obtain the fibers, and then you push the fibers and the length and the tokens, the text tokens, and that's it. So it's just a stacks of transformer, and you can either use bidirectional attention. When you're pre-training, you can use a variety of diverse set of attention schemes. So here you only have mask language modeling and image text retrieval. Image text matching. Just to say, it's exactly the same as Pixelbert. We don't do anything else. You just do mask language modeling for the text part, and then you do image text matching for the CLS token, and that's it. And when doing so, you can either use the full bidirectional attention between the image and the text modality. So you fully attend both modalities at the same time. Or either you can use sequence to sequence image, sequence to sequence attention scheme. So here, what we're trying to achieve is that if you think about the transformer decoder, where the transformer decoder, you use a triangular attention map, right, to encourage decoding behavior. So here you can do similar thing here. When you want to train a pre-trained model for image captioning at the downstream task, you might want to use this kind of attention map. So you want the text tokens to attend fully to the visual embedding, to the image part, but you don't want the text tokens to look into the future. So that's what this attention map is for. And you can use as a downstream. You can use as a baseline where none of the where the two modalities don't attend to each other. So, for example, here the non-crossing attention map, the visual embedding or the image tokens are only attending to itself. So internally, only internal attention here, and the language embedding, the text part, is only attending to itself, and it is never crossing across the modalities. So that is why it's called non-crossing attention here. So here, if you do this, you are actually not fully utilizing the potential, the capacity of the BERT model, because you're only attending to the models are only attending to each other within its own modality. So yeah, so three types of attention maps here, and when you pre-train your model using different attention maps, it has different impacts on the downstream task. So one of the downstream tasks is diagnosis classification. So you provide the pre-trained model, and you need to fine-tune the model for this kind of classification task. But at the inference time, you put the image and the report into the fine-tuned model, and then try to do a multi-label classification, basically, because a single image can be associated with multiple diseases. And when you use different types of pre-training attention masks, they have different outcomes. So here, average AURC and micro AURC and micro F1 score are a bit different from different attention maps. So obviously, non-crossing attention maps should perform the worst because it is not fully utilizing the self-attention capacity of the BERT model. So when you use the fully bidirectional, it shows best performance, and sequence to sequence, not so much. And bi and sequence to sequence is just alternating between bidirectional and sequence attention map when you're pre-training. So for one batch, you do bidirectional attention, and for another batch, you do sequence to sequence. For image text retrieval, this is basically you fine-tune the model to perform image to text retrieval or text to image retrieval, basically. So using the CLS token, given an image and a report, you're trying to generate a score using the CLS token. So whether they're from the same pair or not. So image retrieval is given, for example, given a report, you try to try to find the most relevant image using the CLS token. So you use the CLS token to score a pair of text and image, and then you rank them, and then you select the one that has the highest score. So the performance, so there are two different performance. So text to image retrieval, and there's image to text retrieval, because you can use either as an anchor. And in this case, interestingly, sequence to sequence attention map shows the best performance, but the bidirect, and obviously, again, this non-crossing attention map is showing the worst performance. And if you look at some examples, so this is image text to image. So what you're doing is you're providing a text. So this is the given text here. Given the text here, you want to retrieve the most relevant image from all the images in the training set, or the images in the pool, basically. So this is rank 1, 2, 3, 4. So this is the model predicted that this image is the most relevant image to this report, but the ground truth was that this one was the ground truth pair. Unfortunately, I'm not a doctor, so I'm not sure if this or this or this is all relevant to, or can be associated with this report. But the good news is, at least the ground truth image was in the rank 2. But this is a bit more interpretable for the layman like myself. So I'm not a doctor, but at least we can't interpret what's happening in the image, but at least we can see that whether these three texts are of, like, what more or less contain the same semantic information. So here, fortunately, the ranked 1 retrieved item was actually the ground truth original pair. So here, if you read this, then like it says no visible pneumothorax, tortuous aorta, otherwise normal mediastinum. There are no visible nodules or masses. The axis is grossly normal. Yada yada yada, basically. So what else? Heart size appears upper limits of normal, so heart size is a bit bigger. Yada yada yada. And if you read the second most relevant retrieved text, it says heart size is enlarged. So here, heart size appears upper limits of normal. So heart size is enlarged. It's about the same semantic. What else? There are no nodules or masses. So here it also says there are no visible nodules or masses, and the x-axis are grossly normal. X-axis is grossly normal. So there's a lot of like overlapping information between the first and the rank 1 and rank 2 retrieved text. So I guess this kind of like a indirect indication that the model is understanding what the relationship between the image and the text. Another downstream task is visual question answering. So there is some data set called VQA Rad, which is VQA radiology. So this data set consists of about 3,500 question answer pairs on 300 images, and the images consist of MRIs, X-rays, and CTs. So it's not just X-ray images, actually. It consists of this VQA data set consists of MRI images. So the question is based on MRIs, or question can be based on CTs, or a question can be based on X-rays. And so the questions are usually either open-ended or closed-ended. For example, like, where is the mass and the extra-axial end at the right lung? So this is probably based on X-ray images. And close-ended question is like, is this an MRI of the chest, or is this like X-ray of the chest, or is this something that's like short answer questions, like yes or no questions. And when you fine-tune the pre-trained multimodal model on VQA red, it is shown. So the different attention masks are different types of attention masks are showing different performance, but obviously non-cross is doing the worst job. And interestingly here, bidirectional attention map showed the best performance here. Unfortunately, there is no qualitative example here, but there are some more qualitative examples in the radiology report generation. So in the report generation, simply you just fine-tune the model to perform a masked repeated mask prediction. So here, given an image, you try to predict what the first mask, and then you replace the mask with the predicted token, and then you try to predict next mask, and then replace the mask with the predicted token, and so on and so forth. So that's how you can generate radiology reports. And here, this is a performance, but we'll just skip this. Basically, what the bottom line is that TiNet is the kind of like the most well-known X-ray captioning model, and perplexity is pretty low, but then S2S is as low as TiNet. So that's the core message here. And this is actual qualitative example. So here, this is the given image, and this is the actual ground truth original report written by the physician, written by the radiology expert. So here, the original report says there's like the ET tube tip is something, and then NG tube tip is approximately located with this, yada, yada, yada. So here you can see a lot of tubes here, like this kind of like line along down the throat is this is kind of like a tube that was used for, I don't know, operation or something. And when you ask the model to generate the report on its own, it says the endotracheal tube tip is 3.5 centimeter above the carina, and nasogastric, yada, yada, yada. So the interesting thing is that, endotracheal tube is actually unabbreviated form of ET tube. So ET tube is the abbreviated form of endotracheal tube, and nasogastric tube. So NG tube is nasogastric tube. So the model understands that there are two tubes, and then instead of using ET or NG tube, you can write endotracheal tube and nasogastric tube. So it understands what's happening in the image, and it understands that ET tube and endotracheal tube are interchangeable terms. So that is why it's doing a pretty good job of generating the report. And the same goes with the second example. So this is a given ground truth image and the ground truth report, and it says that the patient has undergone a VATS procedure. So VATS procedure, I'm not sure what VATS procedure is, some kind of like cardiovascular procedure. And instead, the report says the patient has been extubated and the nasogastric tube has been removed. So this is actually a part of VATS procedure. So after the VATS procedure has been completed, the nasogastric tube and all the tubes needs to be removed. So this part is actually subpart of VATS procedure. So the model kind of understands that this kind of thing happened to the patient, although it doesn't say that the VATS procedure occurred explicitly. So again, it's kind of like it kind of understands what the patient has gone through, and it understands it is well generating textual information, how to do it. This is the same attention behavior analysis like from the Pixelbird with dog and carrot images. So here, this is the given image, and this is the given ground truth sentence written by the physician. And it says, moderately severe pulmonary edema is new, and it is accompanied by small bilateral pleural effusion. So pulmonary edema is 폐부종. So pulmonary is like it is related to lung. So there's something wrong with your lung, and these two words, it is attending to this part, this red circle part, and there are some white noise, not a noise, some. So you're originally, if your lung is healthy, then it should be clean. It should be just black, like this guy. But there are some white noises here, which is the pulmonary edema, or at least the physicians told me so. So the pulmonary edema is attending to the right correct region. And the pleural effusion is when there's water being contained in your in your lungs. 그러니까 폐에 이제 그 물이 차는 거, 그렇죠? 물이 차는 겁니다. 그러니까 물이 고이는 건데, 물이 고이면 보통 이제 아래쪽이 고일 테니까 이제 이렇게 밑에 이제 고이게 되는데, 이 플로럴 이퓨전이 제대로 요 아래 고이는 부분을 가리키고 있다라고 이제 제대로 하고 있다고 또 마찬가지로 의사 선생님께서 확인을 해주셨습니다. 그래서 이제 두 개가 pulmonary edema, 이제 pleural effusion. So when the model is being trained with X-ray images and report, it didn't use any domain-specific knowledge. It's just a bunch of pixels and a bunch of text, and that's it. Just hundreds of thousands of pixels image, and that's it. And after looking at a lot of text and image pairs, the model just picked up that pulmonary edema is associated with certain patterns of pixels. And again, pleural effusion is associated with certain patterns of pixel, which is this pixel. So that's why it is starting to understand the medical knowledge. And here, another example. So this is a ground truth image, and this is a ground truth sentence. And here, it says the heart size borderline is enlarged. 그러니까 이제 그 심장의 경계선이 좀 커졌다. 그러니까 심장이 좀 비대해졌다. 뭐 이런 거죠. So in that case, heart size borderline enlarged. So this sentence is attending to this region here, and specifically, the attention is being focused towards this part where the heart is. So this is the heart actually. So the model is attending to the right heart, heart area for this sentence. So again, the model is understanding what's happening here, and is doing a good job of grounding the word tokens into pixels. So if you think about the pre-trained model for image and text, what's impressive, or what's important here, is that no longer the text is just if you think about what we did with NLP techniques, you either use BERT or you either use word2vec or skip grammar, those kind of stuff to do a pre-trained model. And basically what you're trying to do is you're just trying to capture the co-occurrence information between different words or different subwords in a very sophisticated manner. So it's basically which word co-occurs with another word frequently or infrequently, and that's it. That's how you try to capture the semantics of the word, and that's it. So it is still just kind of like ungrounded. So semantic of the word is based on the neighboring words, and that's it. But here, if you try to put both pixel information and the word information at the same time to the model, then the words are no longer just relying on the neighboring words to capture the semantic, but it is also using the pixel information to understand, to learn the semantic information of the words. So the words are now, that is why we call the words are grounded. The words are grounded to the pixel information. It is no longer just doing like a cyclic. If your semantic word semantics is only based on other semantic word semantic, neighboring word semantic, it is kind of like cyclic definition. But here you have a pixel information where you can ground the word semantic information too. So that is why it's no longer just cyclic definition. So that is the power of multimodal learning. And you can do the same with you can do the same with other types of multimodal learning, like graph and text, or graph and image, or even to if you pushing to the extreme, like more than one image per text, 2 images per text, or 3 images per text, or 4 images per text. That you can also do that for grounding the word semantics. All right, I think we're out of time. Yep, and just rightly so. So, any questions so far? So these days, a lot of machine learning work is being toward the direction of the machine learning is multimodal learning with large network, like transformer-based network, especially because of the DALI and GPT-3 and all that. So it's a lot of effort is being towards the engineering part rather than the modeling part, because the model itself is already transformer model itself is already kind of like complete model. It's like the best model that the researchers came up with so far. So it's a really good time to do multimodal learning, even if you're not really good at, even if you're not really like machine learning expert, you can still do pretty large scale multimodal learning if you're good at, and if you have like sufficient engineering skill and just basic knowledge of transformer model, then it's a good time to do multimodal learning. All right, so if there are no more questions, then I guess this is the end of the class today, and I'll see you guys this Thursday, and hopefully please make the deadline for your project number 2. All right, thank you guys, bye-bye.